Alright, welcome to another video tutorial of electronic circuit and design, and today we are going to discuss the issues that we are actually facing in the previous lab. And I hope that you remember this circuit. This is the class B symmetric configuration of the amplifier. uh, Let me just demonstrate you the output so that you would easily remember it, in which we were having the sine wave that was 8 volt peak to peak, and there were a voltage divider circuit that was connected with one of the NPN transistor, and the other one is the PNP transistor. Alright, now let us just simulate this circuit so that we could check that whether there is a problem or not. So I just press the run button, and this is my input. You can easily realize it that it's very much smooth, and we also expect the same type of the waveform at the output as well. Okay, now if you look at into this diagram, the green waveform is the input waveform and the blue is the output. You might observe two differences, one in the amplitude and other one in the biasing, you can say. Now the blue waveform is actually saying that it is not the base to emitter junction is not going to the conduction state at once. Now this means that whether the voltage at the base to emitter junction is not sufficient to cause the diode to get into the forward conduction region at once at once. So let us just realize our circuit so that we can suggest few suggestions that could reduce this crossover distortion. So this is an unwanted desired waveform, and this distortion should be minimized. And when this happens, it actually means that in this state one of the transistor is on and the other one is off, and simultaneously the other one will be on and the previous switch will be off. However, ideally both of these switches must respond in a very fast way so that there might not be such kind of differences. Okay, now let's just check into our circuit that whether we are providing the enough voltage to these diodes so that whether they could move into the conduction region or not. And in the end, let's see how many types of solutions do we have to recover our the input circuit at the output without any sort of the crossover distortion. Okay, now this is our voltage divider circuit that is being connected at the base of Q1 and Q2. One is the NPN and other one is the PNP transistor. Both are assumed to have the same characteristics, so that they must conduct at the same time and at the same specifications. So we need to check what is the voltage that is being going in this path, and what is the voltage that is being in this path. So for to calculate this thing, we previously did the calculation that was we need to find out the voltage at this loop. So we can easily do it by the using the voltage divider rule. Okay, now this is the voltage divider rule says that by the voltage across this resistor divided by the total number of the resistors that are being connecting in the series path. So if this is true, then 680 plus 680 divided by the 10k plus 680 plus 680 plus 10 kilo ohms and multiplied with the DC voltage, in which in our case is 10 volt. So what we actually obtain is over here is, so this means that 0.636 volt is the amount of voltage that is being present in this internal loop. So if there are two base emitter junction, so that means the 0.636 voltage will be divided equally between these two transistors because they are of same specifications and ratings. So each of the base emitter junction will share the equal amount of share. That means the 0.636 will be divided in two parts. Now if I divide it by 2, so it means that the amount of the voltage per the junction will be equal to 0 0.3 and 1 and 8. This means that 318 millivolts will be shared by each of the transistor. So each transistor is having a silicon diode. That means the voltage drop across each of the diode will be 0.7 volts. So I don't really think that the 318 millivolts or 0.318 millivolt will be sufficient to cause the conduction. So that is why you are actually observing the crossover distortion over here, 0.7 volt over here as well. So if by some reason we are able to overcome this problem, that means if each of the diode or the transistor is able to achieve or receive the 0.6 volts, then in that case we will be able to overcome the crossover distortion. So let's just try to first of all we have the two options. We have two options over here. How we are going to overcome the crossover distortion. Solutions to crossover distortions. So we have two types, two methods that could do that. Okay, now we have come to the point where we can propose the solution to this problem. One method is to change the internal resistance of R3 and R4 in such a way that the voltage across these resistors could sum up to such a value that each transistor can share approximately 0.6 volt, so that they could, their base to emitter junction could enter the conduction state very slightly. And the other solution to this problem is that we can connect two diodes in series over here with such a limitation that these diodes will have the same characteristics of that of the base to emitter junction diodes of the Q1 and that of Q2. Only in that case the amount of the current that is flowing through these transistors, one is the Q1 and another one is Q2, will be same as that of the current that is flowing through these two diodes. This situation is actually called as the mirror current, in which you can say that the diodes are and the diodes in the base emitter junction are sharing the same amount of current, and this is only possible if you are sure that the diode that you have installed externally and those one in the transistor are same. Okay, so this is your responsibility. Sometimes the people think that this is quite challenging, but you can easily do that by using the digital multimeter and measure the amount of the voltage between the base and emitter junction. Normally and practically the 0.5 volt is the amount of the voltage drop. So I do believe that the diodes like 4118 are these are the practical diodes that you can actually obtain from the market. They also have the same amount of voltage drop, and in this case if the amount of the voltage is same, then they will be sharing the same amount of current. Okay, now let's just apply these two solutions side by side. Okay, alright, now let us just check what is the amount of voltage that is being over here between the base to emitter junction. Just right click over here, mark it as a reference, and use the second probe. Click over here and you will get the this thing. Now what is actually say that Okay, what is the amount of voltage drop? It's actually 684 millivolts. That means approximately 0.68 volt, and by rounding it off it will be zero point 0.7 volt, which is the ideally the voltage drop across the silicon diode. Okay, now this is the hurdle that you need to overcome it, and the amount of the voltage that you are actually supplying it over here is actually 318 millivolt. Okay, now you can easily check it by using that reference probe, and with that of this one, just click it over here, and this is approximately 318 millivolts, so it's overall constant, so it's not a problem to realize it with the graph. So let us change the resistance now. Now I have fixed the internal loop resistance of 1k over here, and both are same, so that they could share the equal amount of the voltage. Now just place the reference cursor over here and click it over here the once, and this one is the input voltage, this one is the output voltage. So let's check it out that whether the crossover distortion has reduced or not. Okay, uh, let's zoom it. Mm, just let's just check it side by side, so that okay, this one is the input voltage, this one is the output. Now you can see the crossover distortion has been reduced. Let's check the amount of the voltage that is being shared by each junction, and this one is here. Okay, now the magnitude, it says that now the voltage has been raised up to 0.454 volts. Now it is much less as compared to 0.6 volts, so we need to increase the resistances once again, so that we could reduce the crossover distortion once again. Let's check it at 5k. This is a 5k, this one is also 5k, and now the you can easily realize that both the waveforms are synchronized with each other, and almost there is not a single amount of the crossover distortion that is being present over here. So let's just measure the amount of voltage that is being now moving into the each junction. It says it's now 0.774 volt. That is much higher than this practical diode, that's the amount of being required over here. Now each of this diode demands actually 0.68 volt, and now with the help of this incremental resistances, we are actually providing them with the 0.77 volt, that is even higher to cause the conduction. Now you can easily visualize it that in the output there will be no such form of the crossover distortion. This is the input. The output must exactly be you can see that there is almost all the points have been synchronized with this input. So that means that we have actually achieved the solution we have actually presented by using the resistances has actually solved our problem. Now let us try to implement the second solution by connecting the diodes having the same characteristics to that of the base emitter junction diodes. Now you can easily visualize that we have replaced the two resistances in the internal loop with two diodes that are being assumed to have the same characteristic that of the base to emitter junctions. Okay, now let's just apply the run button, and remove the all kinds of extra tabs, and just press the run button. This is the input voltage, and this one is the output voltage. So you can see that all the waveform have been synchronized with each other, but only the difference is that there is a small uh, a minute difference in the output amplitude, and let's check it out that why it is there. Okay, we can now easily use the basic concept from the previous circuit diagram, that if the voltages drop shared by the resistor, if they are not sufficient to cause the conduction, then there might be some issues regarding the crossover distortion and the change in the amplitude as well. So previously we were supplying the 0.77 volts to cause the good conduction to the base emitter junction. Now presently we are using the two diodes, and we also demand the one thing, that they must have the equal amount of voltage. Okay, now you can see that the junction base to emitter junction of each of the diodes is demanding the 686 millivolt, and if each diode is capable to deliver this voltage or higher than this, only in that case the amplitude and the output waveform will be synchronized. Okay, now let's check it out, that what is the voltage drop across each of this diode. Now if I see, it actually says that you can see that 0.547, that means the 547 millivolts. It is actually lesser than that of the required base to emitter junction. So here what you can do is that you should try to find out the diodes that have exactly the same characteristics to that of the base to emitter junction. If you are able to do that, only in that case the output will be exactly same as that of the input. Okay, and this is the today's tutorial regarding to the present the solution, and how you can easily cover up the crossover distortion. Okay, most of the cases people use the first type of this solution, that is the change in the resistances, and sometimes it is not advantageous because of the power dissipation, and due to the availability of the diodes, which are very fast in switching, and they have also a very good characteristics, so they are actually most preferable. But in practical cases, most of the time uh, people are not able to find out the exact match of the diode that could be easily matchable with the base emitter junction diode. So this is the main issue when you are actually installing this scheme, implementing this scheme with the to reduce the crossover distortion. So it's up to you, whatever the strategy you want to apply, you can apply, and this is a task for you. And if you are able to find the specific diode available from the LT Spice library, and I can assure you that it is available, you can easily find it out by going to this LT Spice, and just open the desired the characteristic of this the properties of this diode, and click on the pick new diode. Okay, now you have various types of diodes over here. There are models over here. What you can do is that you can click on the model, and you can easily read out the properties that are being presented over here, and most easily sometimes the voltage drop property might not be mentioned in this model. So what you can do is that you can find out the specific diode with the 0.6 voltage drop, and using the data sheet analysis, just fix that number and come to this library, and you can easily find that particular diode over here. So it almost has all the types of the data sheets models and those practical diodes, so you can easily find them over here. Okay, so let's meet you the next week with new task, and I hope so that you really enjoyed this video. If you have any question, you can easily comment it below in the section, or you can email me in the email provided in the description. So thank you very much.